Hey everybody, this is the second video of my What is the Derivative little mini-series basically. In the first video I talked about what a derivative tries to find, and I talked about one way of figuring out the formula for a derivative. Today I'm actually going to give a second formula for the derivative and talk a little bit about how to compute the derivative. So, I talked about, I guess I can give a visual example here. If you take some function, let's say we can make our function look like that, call this f, and what we're trying to do, let's say if we want to measure the derivative of f at this particular point, what I said is we can take another point, and I'll call this, I guess we can have this little red point here, and we're going to measure the difference between those 2 points, and then shrink that difference until it's pretty much 0. Not exactly 0, but pretty much. That's one approach. The other approach is actually saying that this x value is moving closer to the other x value. They're very related, those two approaches. They're very similar to each other, but it's just a slight little reshaping of the question that'll give us a slightly different formula, basically. I've shown in a previous video that they are equal to each other. Those two formulas are equivalent, but that's not really important for now. I just want to show you another construction of the formula for the derivative. So, I'm going to call, so this is the point we're trying to measure the slope of the function at. So I'm going to call this a comma f of a, and I'm going to call this red point x comma f of x. So x comma f of x. Okay, so one thing I wanted to say is that this red point is going to move. It's going to vary depending on the value of x. Okay, and we're going to move it closer to this other point. In the last video, yes, the red point did move, but the black point was called x comma f of x, okay? The difference here is that typically the formula that I'm about to share with you is used when you're actually trying to compute the derivative at a point. The formula from the last video, it can be used to do that, but it's not very common to actually evaluate the derivative at a particular point using that formula. That formula is usually used, and it's easier to use whenever you're trying to evaluate the derivative of the function over its entire domain, which gives you a function, a new function as the answer. Here we will always get a numerical answer, and it's really hard to reframe the construction of the formula so that it gives you a functional answer. So this formula is pretty much reserved for if you're trying to evaluate the derivative of a function at a particular point, okay? And that point is going to be x equals a, all right? So what we have here, we can, again, just do the same thing of computing the slope. So let me call this point 1 and this point 2. And we're going to take the slope between these 2 points. So we have this one minus that one, so the difference in the y's is f of x minus f of a. And now the difference between the x values is just x minus a. That's it. So that's our difference quotient. Now what I'm going to do is basically just move this x value closer to that other x value. So what I'm going to do, so this is point 1 there, I'm going to draw some dotted lines down here and down to here, and I'm going to move this x value so that it's precisely equal to a. So this is a here. And by doing that, I'm also moving the f of x value so that it goes up to the level of f of a. And by doing both of those actions, we are essentially moving this point so that it's going all the way there until it actually hits our desired point, a comma f of a. And so what we're really doing, so what initiated this whole motion is just me saying that this x value is going to a. So that, in other words, we're taking x and we're moving it closer to a. So x approaches a, and that's our limit. So we're going to take the limit as x approaches a. And this is another definition of the derivative. And this, I guess I shouldn't have circled it already. This is equal to f prime of a. So the derivative evaluated at the point a, pretty much. And so this formula and the formula from the last video, they're the same thing. They measure the same thing. They have basically a slight change in the perspective that you're viewing the problem from, and that's pretty much it. So now, we can try to work with some examples. So we can use, let me actually write down both formulas. So I'll clean the board up, write down both formulas, and then give some examples. Okay, so here I wrote down the two limit definitions. So here, this is the one that's reserved, but not reserved for functions, but typically used for functions. Here it's for a numerical answer where we're trying to find the derivative at a point a, okay? So our first question asks us to find the derivative of f of x equals x squared. So we actually cannot use the second formula because it just doesn't work. If you try to plug things in, it doesn't really work. We have to use the first formula to figure this out because we're not trying to evaluate it at a particular point, it's just over its entire domain. So I can start, so what we're going to do is think of f prime of x. So this is going to be the limit as h approaches 0 of f of x plus h. Well, if f of x is x squared, then f of x plus h would be x plus h squared. So this is x plus h squared, and then minus f of x, well that's easy, that's just minus x squared, and then divided by h. Okay, so what we can do here is expand this x plus h squared out. So before I do that, let me just write down again, limit as h approaches 0. Always keep that until the last step. So now we're going to expand this. This is going to be x squared plus 2xh minus h squared, plus h squared, and then we're going to do minus x squared, right, because that just follows from here, and then all divided by h. Okay, so now we can do a little bit of cancellation, so we can notice that x squared and x squared cancel, because x squared minus x squared, and then now we're just left with this in here, so 2xh plus h squared over h. All of those have an h, right? So we can cancel one h here, one h there, and then one of these h's. So instead of h squared, now we just have h. And so let me write down what we have now. We have the limit as h approaches 0 of 2x plus h, right? So 2x plus h. Well, as h goes to 0, that just goes to 0. And we are left with just 2x. So now I don't write the limit anymore because this is our final answer, and it is 2x. So the derivative of x squared is 2x. Now we can do, I guess this is like a part A, and this is a part B. Now we can find the derivative of f of x equals x squared at a particular point. So, I can do ... here at, let's say, x equals 5. So we're finding the derivative of f of x equals x squared at x equals 5. Well, that's easy. So we just say 2 times 5, that's 10. And all I did was just plug the 5 into here, and then that's our answer. We could have done that from the start. If they asked us, we could have just said 5 plus h squared minus 5 squared over h. That wouldn't really have simplified much of the computation, but it is possible, okay? Let me give one more quick example. Actually, we can continue with this example. Let's say we wanted to figure it out at x equals 5 using this formula. So let me just erase my current work here. Okay, so now 5 is pretty much our a value, and we can plug this in. So we have f prime evaluated at 5, and this is just going to be the limit. So limit as x approaches 5 of f of x minus f of 5. So f of x again is x squared minus f of 5. Well, that's just going to be 5 squared, which is 25. And then all divided by x minus a. So x minus a, which is 5. And so here we have, again, a limit that we have to evaluate. So we can think of limit as x approaches 5 of, well, if you may notice that this is just going to be x minus 5 times x plus 5. So x minus 5 times x plus 5. And that's because we can think of this as x times x is x squared, minus 5 times 5 is negative 25, and then the middle terms cancel out because we have minus 5x and then plus 5x. You can verify that for yourself, but they do cancel out. And then down here we just have x minus 5. And if you notice, again, we have some cancellation. Usually happens with these types of problems. X minus 5 cancel out, and now we are left with the limit as x approaches 5 of x plus 5. And so now as x approaches 5, we can just plug 5 in, so this is just going to be 5 plus 5, and again we get 10. So notice how we get the same answer as before when we did the other method. And yeah, so we do this. Again, just remember, we can't just plug x equals 5 in at the very beginning, because then that just will end up, if we plugged that in first step, we'd have 5 squared minus 5 squared over 5 minus 5, which is all 0 over 0, which you can't actually do. So we have to wait to actually plug in everything until everything's fully simplified. But yeah, so that's a little more about the derivative. Don't worry, you won't have to do these limit computations every time. Eventually you'll be given some other formulas, and you can actually figure out and derive these formulas from the limit definition. I have a bunch of videos on that on my channel. Probably a little bit advanced for now, but if you want to check them out, I'll leave them as a link in the description. But yeah, I hope you guys enjoyed. Thank you so much for watching, and I'll see you in the next video. Bye guys!